This lesson deals with Supplemental Problem 12.1. You can find this problem in the ECE202 ebook in the Chapter 12 Supplemental Problems starting on page 1. Given this RC circuit, can you solve for V out of S over V in of S, sketch the Bode plots, and verify with PSpice, and then draw the results of Part B on the output plots? To save some space, I showed the SPICE file first, and let me just go through it real quickly. So here I have a title, and a dot end, dot probe, and then a description of my schematic. My voltage source is between 1 and 0 and has a value of 1, and it's an AC phasor. The resistor R1 is between 1 and 2, has a value of 4.7K. Capacitor C1 is between 2 and 0, has a value of 0.02 microfarads. And then lastly, R2 is between 2 and 0 with a value of 6.8K. We'll see on the following pages that our frequency response roughly goes from about 100 Hertz to 100 kilohertz. So I've got 3 decades. If I divide that by 200, I get roughly 66 points per decade. What's V out? Well, it's a voltage divider with this impedance, voltage divided with R1. Let's take the admittance and add it together and then take the reciprocal. So the admittance of the capacitor is SC1 and the admittance of the resistor is just G2. Let's multiply numerator and denominator by SC1 plus G2. So I get a 1. I get a 1 here, and then I multiply this times this term. And that's going to be this, SC1R1 plus R1G2. Let's next multiply the numerator and denominator by R2, and I'll get rid of this G2 term. So I have an R2 in the numerator, and then I have SC1 R1 R2. R1 times G2 times R2 is just equal to R1, and then 1 times R2. Let's divide out this term C1 R1 R2. I'm left with just S, and then I'll have R1 plus R2 divided by that. And in the numerator, likewise, I'll have R2 divided by C1 R1 R2. The R2's cancel. I have 1 over C1 R1. Putting in the value for C1 of 0.2 microfarads and R1 of 4.7K. And likewise here for our values of R1 plus R2 and R1 times R2, the 4.7K and the 6.8K. Numerator term turns out to be 10.638K, and the denominator term 17.991K. To do our Bode plots, we need to replace S by j omega. So our transfer function then becomes 10.638K divided by j omega plus 17.991K. We need to make this look like our form, so I need to make this equal to a 1. So I'm going to pull out a 17,991. And likewise from the numerator, the 10,638. So I'm left with 1 divided by 1, and then j omega divided by 17.991K. I've got a product of two terms, a form 1 and a form 5. So the first term, 20 log of that, turned out to be minus 4.56, which is a straight line. And then our form 5 has an omega c at about 18K. So below 18K, I have a slope of 0 dB per decade, and above it, minus 20 dB per decade. So adding these two together is just simply shifting this form 5 down from 0 dB to minus 4.56. Phase angle of the first term is 0. The phase angle of the form 5 then is to be down 45 degrees at about 18K. Go back a decade to 1.8K, have 0 degrees. Go forward 1 decade to 180K, and we're down to minus 90 degrees. So I don't normally work in radians per second. So pulling out a 2 pi from the 17.991K, we wind up with a frequency of 2.863 kilohertz. Let's compare this now with a simulation. In my first plot, I plotted node voltage 2. Now since the input is 1, the ratio of the output to the input is just node voltage 2. So I'll do that in dB, and here's the actual smooth curve. The value at low frequencies was a minus 4.567. I found the frequency 2.863K using my ruler and a technique described in the Chapter 12 notes, and then drew my asymptotic approximation. So below here, 0 dB per decade, and then a rate of minus 20 dB per decade. And I'm basically down 3 dB at this frequency. To do the phase angle, take the phase angle of the numerator minus the phase angle of the denominator. The input is just an angle of 0, so it'll just be the phase angle of the numerator of our transfer function, which just be node voltage 2, so that'd be V sub p of node voltage 2. You can see the actual curve going from 0 degrees to roughly minus 90. My ruler I found where 2.863 is, and then went back a decade and then forward a decade, and I drew in my asymptotic approximations. And you can see here that I passed through 45 degrees at about 2.863K. And this is Supplemental Problem 12.1.